Hello students, I am Pavan Kumar Bandoji, working as an assistant professor in the Electronics and Communication Department at the National Institute of Engineering, Mysuru. So first of all, I welcome you all to this course, a 5-day workshop on analysis of linear systems. So a brief introduction about the flow of this workshop. So I am going to take off with the definition of signal. Okay, so and then I'll classify into two important uh, I'll divide them into two important parts. Okay, so next I'll move on to define what a system does. Okay, and then I'm going to look at the two important properties, that is the linearity as well as the time variance or time invariance, right? So this time invariance property as well as linearity property is important because in the courses that we are going to study, may it be communication or your controls or your digital signal processing, so we are going to, or analog electronics, network theory, right? So we are going to look at or model the systems as linear and time invariant so that the analysis becomes easier, right? And then after this, so I'm going to define two important signals, right? So one is called the unit impulse signal, and the second one is the unit step. Okay, and then I'm going to uh, emphasize the importance of the linearity and time invariance, okay, in deriving the relation between the output as well as an input of an LTI system, a linear time invariant system. Alright, after that we'll move into the Fourier analysis, and I'm going to explain or emphasize on one important property called as a modulation theorem or modulation property, right? This property covers your whole of communication except for the noise part, right? So if we assume that there is no noise, so the whole of communication is covered using, or is basically application of your modulation property of Fourier series or Fourier transform basically, right? So next I'll define two important, as I told, so a unit impulse and unit step, and I'm going to tell you about the relation between those two signals. Okay, and the importance, why unit impulse is so important. Okay, so after that I'm going to do the Fourier analysis. Okay, so then I'll move on to what is called as the Laplace transform, right? So this is one important topic uh, which you'll see throughout your course in network theory as well as your control systems, right? Analog control systems. So it's basically nothing but using the Laplace transform in different ways. Okay, so to study the systems basically. Okay, and the last topic, and I'm going to emphasize on the geometric evaluation of a Laplace transform or geometric interpretation, right? And then it's nothing but a complex number, so no rocket science there, right? And next I'm going to go into the what is called the Z transform, which is nothing but a discrete time equivalent of your Laplace transform, right? So, and I'm going to outline two simple systems, right? So basically a digital filter. Okay, so and I'm going to tell you how to evaluate the response, a frequency response of a digital filter geometrically, right? So basically geometrical interpretation in Laplace transform as well as in Z transform, right? So Z and Laplace, they're nothing but two complex numbers, right? One is in the rectangular form, the other one is in the polar form. Okay, so no nothing that you have not learned previously. Okay, so to start off with, so the definition of a signal. So what do you mean by the term signal? A signal is nothing but a phenomenon that conveys information. Okay, so Mathematically we represent signal as a function of time, right? So in this course we'll be looking at signals as a function of time, right? So and a signal may be of any form. For example, your the sound waves that you produce, right, when you talk is nothing but an acoustic signal. Okay, so the variations in pressure will be perceived by your ear, and that's what you hear. Okay, so mathematically in this course we'll be looking at signal or describing the signals as a function of time. Okay, and the notations that I'm going to use are basically x of t, right? So where t is the independent variable. So these all these things you know, right? And usually I'll be using these two notations, right? So x of t as well as y of t, or the argument. The t here is called as an argument, so the argument can change, right? So depending on the domain that I'm in, I'm going to explain these terms. Okay, now next comes the classification of a signal. Right, so there are different ways the signal is classified. So for a deeper understanding of this, so you can refer to a textbook called Signals and Systems by Alan V. Oppenheim and Wilsky, I guess, the second author. Right, so a thick book, which is a very good book referred in all the good universities. Right, so you can dig deeper if you are so interested in these topics. Right, so one important classification is, so I'm going to classify these signals as analog signals and digital signals. Okay, so what do you mean by the term analog signals? So there are two kinds. So one is a continuous time, continuous amplitude signals, right? So they are basically written as continuous time signals. Okay, here, so the time as well as the amplitude can take a continuum of values. Okay, right, so I'm going to draw a random signal. Okay, so if this is my x of t, the y ordinate, right, the time is my x-axis, right? So the time can take any value on this x-axis, okay, which we are used to in calling this the horizontal axis as a x-axis, right? It can take any values here, right, as well as the amplitude can take any values on this line. Okay, so from minus infinity to plus infinity, there is no restriction. Okay, now, so there is another classification of analog signals called the discrete time signals. So they are not signals as much as they are sequences. Okay, so a discrete time signal or a sequence, right? So I'm going to use the word sequence from now on for all the discrete time signals, because it is nothing but a sequence of numbers, right? Here, so I have two axes, right, and the convention is to use the term n, right, for the x-axis, right? So the term n is used for the x-axis. Now the difference here is between the two, there is a restriction on the values that a n can take, right? So n can only take the integer values. Okay, so on and so forth. So this is minus 3, minus 2, minus 1, 0, 1, 2, 3, 4, 5, so on and so forth on the right side as well as the left side. Okay, so there is a restriction on the x-axis here, but there is no restriction on the values that the amplitude can take. For example, so it's usually represented with a dot on the top, Okay, so this is my x of n. So n is not a time, not related to time, it's basically an index. Okay, so it just represents the position of a number in a sequence. Okay, so we can take 0 as a reference and then define the position of all the other numbers uh, with respect to the 0 reference, right? So if you do that, so let this value be here 1.23, right? So this will be 0.98. Okay, so this will be minus 1.5638, so on and so forth. Okay, so I'm just writing some random values here. Okay, so what I'm trying to emphasize here is that there is no restrictions on the values that the y-axis can take. Okay, so it can take all the values between minus infinity to plus infinity, whereas your x-axis has a constraint that it can only take the integer values. Okay, so x of 0, let it be equal to some 3.856. I'm writing some random numbers. Okay, there is no relation. Okay, as such, no importance given. All I'm trying to emphasize is that my x-axis can take only the integer values. Okay, so there is no value in between 0 and 1, between 1 and 2, so on and so forth. But the amplitude here, which is represented by the y-axis, can take all the values, right? Any values that lie here. Okay, from minus infinity to plus infinity. Okay, so this is my analog signals. So these two are the type of analog signals, right? And the second one is nothing but a digital sequence or a digital signal. So right, so the difference between the discrete time as well as the digital sequence, discrete time sequence as well as a digital sequence, is nothing but there was a constraint on the x-axis and there was no constraint on the y-axis in the discrete time sequence case, right? But whereas in the digital sequence there is a constraint on both the x-axis as well as the y-axis. The x-axis can take only the integer values, whereas the y-axis can also take values, right? But not any value between minus infinity to plus infinity, a fixed set of values. Okay, for example, here if I'm going to represent it on a plane, so have x of n, right? N is the same in both the discrete time case as well as the digital case, right? You have n here, right? So the values, so this is 0 as usual and this is 1, 2, 3, 4, so on and so forth. This is an index, right? So hence it can take only the integer values. Okay, so if I start writing the values of y-axis, right, it can take only specific values. Okay, let's say this is 1.25. okay, so this is 0.5, so this is minus 1.5. Okay, so on and so forth on the left and so on and so forth on the right. Okay, so if you notice the difference between the discrete time sequence as well as the digital sequence here, right? So your y values in a discrete time case were taking some any value on the y-axis, right? So there was no restriction as such. But if you notice the values of y-axis in a digital sequence, right? So they can only take, they are taking the values which are integer multiples of value 0.25. Okay, there is a restriction. There is no value between 0.25 and 0.5. Okay, so the sequence can take the y-axis values are also having a constraint that the values of y-axis should be multiples of integer multiples of the 0.25. This is just an example. right? So it can be multiples of 0.5 or any smaller number, right? 0.05, 0.0